Okay, 3.4 is measures of position and outliers. So in 3.1, we determine measures of central tendency, which describe the typical data value, the average. In 3.2, we discuss measures of dispersion, which describe the amount of spread in a set of data. In this section, we're going to discuss measures of position, which describe the relative position of a certain data value within the entire data set. So let's just think about an example. Let's say at the end of the 2014 season, the Los Angeles Angels led the American League with 773 runs scored, while the Colorado Rockies led the National League with 755 runs scored. It appears that the Angels are the better run-producing team. However, this comparison is unfair because the two teams play in different leagues. The Angels play in the American League, where the designated hitter bats for the pitcher, whereas the Rockies play in the National League, where the pitcher must bat, and pitchers are typically poor hitters. So to compare the two teams' scoring and runs, we need to determine their relative standings in their respective leagues, right? So we can do this using a z-score. The z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data value and then divide by the standard deviation. We have a population and a sample z-score. Of course, that just means which mean and standard deviation are you using, but it's the same process. Now, if a data value is larger than the mean, the z-score is positive. If the data value is smaller than the mean, the z-score is negative. If the data value equals the mean, what do you think that means? Yeah, the z-score is 0. A z-score measures the number of standard deviations an observation is above or below the mean. For example, a z-score of 1 means that data value is 1 standard deviation above the mean. A z-score negative 1.5 means that data value is 1.5 standard deviations below the mean. So the z-score provides a way to compare apples to oranges by converting variables with different centers or spreads to variables with the same center and spread. So let's look at an example. Okay, the mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. So data is based on information obtained from the National Health and Examination Survey. So who is relatively taller? Kevin Garnett, who's 83 inches tall, or Candace Parker, who's 76 inches tall? Well, if we just said who's taller, you'd say Kevin. But think about this, since Kevin's a male, males are generally taller than females. So what we want to do is compare them relative to their gender, right? We're going to do that using a z-score. So remember our z-score formula. Let me get my pen here. Okay, so let's find the z-score for Kevin. Okay, so we take the data value, which is 83. We're going to subtract the mean. So since he's male, we're assuming, okay, is 69.1 and divide by the standard deviation of 2.8. Okay, and then let's find the z-score for Candace. So she's 76 inches tall. We're going to subtract the mean height of females and divide by their standard deviation. All right, find my calculator. So let's see what we have here then. Okay, 83, and again, don't forget your parentheses, right? 83 minus 69.1 divided by 2.8 is 4.964. And for Candace, we have 76 minus 63.7 divided by 2.7. 4.556. So in this example, not only is Kevin physically taller, he's also relatively taller, right? Okay, so that's what z-scores are used for, to compare apples to oranges, right, based on the same scale. Now, be careful with negative z-scores, because suppose your z-scores involved Kevin and Karen running a marathon, right? Who's the fastest? In that case, even though Kevin scored, let's say that we wound up with a negative score, okay, even though Candace's score is larger, right? Negative 4.5 is larger than negative 4.9. We would still say that Kevin is relatively faster because he's farther away from the mean. So be careful with those negative scores. Okay. Okay, percentiles. Recall that the median divides the lower 50% of a set of data from the upper 50%. So the median is really a special case of a general idea called the percentile. So the kth percentile, denoted P sub k, is a set of data. Oh, the percentile of a set of data is a value such that k% of the observations are less than or equal to the value. Okay, so think about this. Percentiles divide the set of data into 100 parts, right? A percent is 100%, right? Okay, so P sub 1 is the bottom 1% of the observations. P sub 2 is the bottom 2%. P sub 3 is the bottom 3%. Okay? Percentiles are used to give the relative standing, here's that word again, relative, standing of an observation. Many standardized exams, like the SAT, use percentiles to let students know how well they scored on the exam in relation to all other students who took the exam. Okay, so percentiles are opposite of what a lot of people think sometimes. If you make in the 90th percentile, it doesn't mean that you got 90% of the information correct on your test. It means, hey, you scored higher than 90% of the people that took it. Even if you made a 42, if 90% of the people made less than 42, you'd be in the 90th percentile. Okay, let's look at an example. Okay, the Graduate Record Exam, the GRE, is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission. Okay, interpret this admissions requirement. Well, that's what we just said. The 70th percentile is the score such that 70% of the people who take the exam scored worse. 30% scored better. So in order to be admitted to the program, an applicant must score as high or higher than 70% of the people who take the GRE. Okay, it has nothing to do with the percent of questions you got correct on the exam. Now, it really doesn't make sense to talk about percentiles other than quartiles for small data sets, because think about this, if you only had 40 observations, how could you divide it into 100 parts? Okay, so when the data sets are large, it makes more sense to determine percentiles using a model, such as the normal model. We've already mentioned that at least once. We haven't really talked about it, but I think I mentioned that we'd be talking about it. So for that reason, we're going to postpone talking any more about percentiles until we can talk about the normal distribution. So we're going to talk instead, focus a little more on quartiles. The most common percentile is a quartile. Quartiles divide the data set into fourths, or 4 equal parts. Okay, so the first quartile, which we call Q sub 1, is the bottom 25% of the data, right? It's like the 25th percentile. The second quartile is the same thing as the median, because 50% of the data is below it, 25 and 25. Okay, in the third quartile, you've got 75% of the data below it, 25% of the data above it. Okay, so to find quartiles, excuse me, let me get a pen. You're going to arrange the data in ascending order and find the median. Okay, or that's the same thing as saying find the second quartile. And then we're going to divide that median is going to divide the data into 2 halves, and we're going to find the median of each of those halves. That'll be the first quartile and the third quartile. All right, so this data, yes, is already in ascending order. So it is the recorded speed of 14 randomly selected vehicles in a construction zone. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 plus 1 is 15 divided by 2 is 7.5. So my median is at 7.5. 1, 2, 3, 4, 5, 6, 7.5. Here's the median. That means the second quartile is 32.5. Halfway in between 32 and 33. Okay, now that gives me 2 sets of data, and I'm going to find the median of this set. 1, 2, 3, 4, 5, 6, 7. 7 plus 1 is 8, divided by 2 is 4. 1, 2, 3, 4. Here's the first quartile. Okay, so there has to be, because of what this means, also 7 values over here. 1, 2, 3, 4, 5, 6, 7. So 8 divided by 2, 1, 2, 3, 4. The third quartile is 38. Okay, so what that means is 25% of these data values are below 28. 75% are above 28. 75% are below 38. 25% above 38. Half of the data is below 32.5. 50% or half of the data is above 32.5. Okay, so quartiles. Okay, if we wanted to, we could find these quartiles on our calculator. Okay, so remember how we went in to find the mean? So let's try that right quick. Okay, so we hit our stat button, and then we choose edit. I have a list in there, so make sure you get rid of the previous list. Go up into the heading, hit clear, and then when you move down, it'll disappear. Go over to your other lists, delete out all your lists, and then go back to list 1 and enter your information. So 20, 24, 27, 28, 29, 30, 32, 33, 34, 36, 38, 39, 40, and 40. Okay, and it tells me there's 14 data values entered, so I feel comfortable with that. Then we hit the Stat button again, move over to Calc, hit one variable statistics, and hit Enter. Now, all you have to do, and notice there's our mean, there's the sum of x's, the sum of x squares, our standard deviation for sample and population. And if you hit your arrow and scroll down, look what you have. The minimum value is 20. Q sub 1, in other words, the first quartile is 28. The median, or Q sub 2, 32.5. Q sub 3, 38. So you can also do that on your calculator. But once again, we've probably already said that it's nice to physically see it before we just start plugging in and only using our calculator. Okay. So far, we've discussed 3 measures of dispersion: the range, the standard deviation, and the variance. All of those are not resistant, remember, but quartiles, on the other hand, are resistant. For this reason, quartiles can be used to define a 4th measure of dispersion, and that's called the interquartile range, or IQR. Okay, and all we do is subtract the first quartile from the 3rd quartile, and that's going to give us the middle 50% of the observations of the data set. Right? So, if we wanted to determine and interpret the interquartile range of that speed data we just had, I've still got that on my calculator, so all I have to do to find the IQR, interquartile range, is take the 3rd quartile minus the 1st quartile, and 10. The IQR is 10. Okay. Notice what that means. That means 50% of the data, right, is between 38 and 28. So the interpretation is similar to the range and standard deviation. That is, the more spread out the data is, the larger this number is going to be. Okay, let's suppose a 15th car travels through that construction zone at 100 miles per hour. How does this value impact the mean, median, standard deviation, and interquartile range? Okay, so, and here's, we're not going to physically calculate them. We've already got them done for us. Let's just compare. Without that 15th car's 100-mile-an-hour speed, the mean was 32.1, the median, which we calculated, 32.5, standard deviation, interquartile range. But if we added one more value, look how much the mean changes, right? Which we talked about that. It would pull it in that direction. The median doesn't really change, 32.5 to 33. The standard deviation also, wow, really changes. IQR, not so much, 10, 11, right? So, which measures do we report? Depending on the shape of the distribution, if it's symmetric, use the mean and the standard deviation. Okay. But if it's skewed right or left, right, those are the data sets that's going to pull our mean and affect our standard deviation, so use the median and the interquartile range. So for the remainder of this course, the direction describe the distribution is going to mean describe the shape, symmetric, skewed right, skewed left, stayed at center, using either the mean or the median, and its spread. the standard deviation, or IQR. Okay, when performing any type of data analysis, we should always check for extreme observations in the data set, like that 100 miles per hour we were just talking about. Extreme observations are referred to as outliers, right? Outliers. Outliers can occur by chance because of error in the measurement of a variable, during data entry, right? A typo, or from errors in sampling. But they don't always have to occur because of an error. Okay, sometimes extreme observations are common. Let's see, for example, say we were talking about, say our data set consisted of the prices of European cars. And if we took a sample of 5 cars from the population of all European automobiles, and if one of those happened to include a Ferrari Spider, well, that's probably going to be an outlier, okay, because it costs way more than a typical European car, but it's not an error in the data. So just be careful. Outliers distort both the mean and the standard deviation because neither of those two are resistant. So because these measures often form the basis for most statistical inference, right? The mean and the standard deviation, that's what we use most often. Any conclusions drawn from a set of data that contains outliers can be flawed. So really be careful about your outliers. As a matter of fact, we can determining and interpreting the interquartile range. Okay, did we miss the slide? I did. I went straight past it without going over it. Okay, I got busy talking about something else. So here we are, checking for outliers. Step 1, determine the first and third quartiles of the data. Step 2, compute the interquartile range. Step 3, determine the fences. Fences are our cutoff points for determining outliers, right? If it's over the fence one way or the other, it's going to be an outlier. Okay, so now let's check the speed data for outliers. So step 1, remember, was determine the first and third quartiles. So we have that already. We have that information. Step 2, you find the interquartile range. We also have that. Now, to find your fences, here's the formula we want to put on our list. It's the first quartile minus 1.5 times that interquartile range. So, right, I know it's written right there, but sometimes it just helps to see it. The first quartile minus 1.5 times the interquartile range. And the upper fence is the third quartile plus 1.5 times the interquartile range, right? So apparently that's 13 and that's 53. These are our fences. Any values above 53 we consider an outlier. Any values below 13 would be an outlier for this set of data. Now, notice this is the data without the 100 mile per hour speed in it, but if it was included in here, this first and third quartile and the IQR isn't really going to change that much. So we would see that, oh yeah, 100 miles per hour is an extreme outlier for that data set. Okay, that wraps this one up. One more section for chapter 3. Let me know if you need anything.